R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on oscillations and waves. In this lecture, we are going to learn the concepts related to forced oscillation and the solutions pertaining to forced oscillation, and also the concept related to resonance. This is the outline for today's lecture: forced oscillation, transient and steady state solutions, and also resonance. We are aware of the kind of damping happening in oscillations. We have got familiarized with the types of damping, namely over damping, under damping, critical damping, etc. All the oscillations happening in the air medium will definitely get damped. There are two reasons for such a damping. One is the air resistance and the second one is the friction at the point of contact. With respect to that, the point the body oscillates. When the damping is present in any oscillation, the oscillation will not happen forever. It will cease at a point of time. If we are able to give the energy back, what is the energy it loses at each oscillation? If we are able to replenish the energy, give the energy necessary for sustaining the oscillation, then it is called a sustained oscillation. We can call such a oscillation which is made to happen forever as free oscillation. Now, how do we make the oscillation happen forever? By giving an external force, that is what is called forced oscillation. This entire lecture is devoted to understand the concept related to forced oscillation. We will actually give a mathematical treatment to the analysis. Let us see what we have. This is the familiar equation which we have already seen. This has the oscillatory term and also the damping term. If an external source can apply energy to the damped system to make the oscillation continue, in that case the oscillation is called the forced oscillation. We are externally trying to give some energy back to it at a particular sequence, because it is its oscillation where the energy itself is varying between the potential energy and kinetic energy continuously. So, we also have to replenish the lost energy in each oscillation by some external means. In that case, we call the oscillation as a forced oscillation. Now, the question comes to our mind: the oscillation will happen at a particular frequency and we also have to give the energy back to the system at a particular rate. Should it be done at the same frequency, or can it be given back to the system at any desired frequency? All these we are going to understand in this lecture. So, let us see what about the frequency at which the energy is given back. Let us have a look at the equation which is pertaining to the forced oscillation. See, we are familiar with the two terms on the right hand side. This is responsible for the oscillation and this is responsible for the damping, and along with that we have another sinusoidal function, the f naught cos omega t, because left hand side we have the force term, mass multiplied with the rate of change of velocity, this is acceleration. So, the left side term is the force, each term on the right hand side is also the forces. So, this f naught is the force that is applied at a oscillating form, and this omega is the frequency at which the force is applied. So, I would like to highlight the term that we have in addition to the regular equation, which makes this equation as a equation for the forced oscillation. The f naught cos omega t term is the term that we have in addition, which takes care of the periodic way of applying the force. A periodic force can periodically replenish the energy to the system so that the oscillation is sustained. This kind of oscillation is called forced oscillation, or there are other names like driven oscillation or sustained oscillation. Though there are mild differences in the term sustained oscillation and driven oscillation, they come as special cases, but all together we can call this as a forced oscillation. We are making the oscillation to continue forcibly by periodically applying force from external source or give the energy at a particular rate. Now, in the content we have the periodic force can be applied in two possible ways. The force is applied at the natural frequency omega naught of the oscillating system itself, or the force can be applied at a frequency omega d of the driving force. As I have mentioned, there are two possibilities. The system itself will have a natural frequency that is marked here as omega naught. The rate at which that we apply the force or the energy is supplied, that would happen at a particular frequency, that is represented here as omega d, the driven frequency. So, this is what is mentioned here as omega d. So, there are two possible ways in which the force can be applied. What will happen if we apply the external force, the oscillating force at a frequency which matches with the natural frequency? That also we will take it up as a special case. What will happen when it is applied at its own driven frequency, when there is a change or a different frequency at which the force is applied? The two effects are different, let us see what they are. In the first case, where the applied force is at the natural frequency of the oscillating system, the system will oscillate at its natural frequency without getting affected. It will be a special kind of oscillation that needs to be discussed separately. It is difficult to give the energy at the natural frequency of the system, that too in phase with the oscillation. Though we have easily mentioned, we just have to apply the external force or give the energy back to the oscillating system at its natural frequency. It is little difficult, though it is easily mentioned. Practically applying the force at the exact frequency at which the oscillating system has a natural frequency is difficult. We need to give it with a minute precision. And another thing also we should keep in mind, when we replenish the energy in the form of applied force, there is damping present in the system, that also we have to keep in mind, because the earlier equation what we have seen, on the right hand side we have the three terms still. One is responsible for the oscillation, the second one is responsible for the damping, the third one is only the external applied force. So, all the three are present. So, when the three forces, three terms are present, we apply the third one. So, it is applied at the natural frequency of the oscillating system, the system will continue to oscillate at its natural frequency. It will happen. There are some special cases to be taken up. Towards the end of this lecture, I will address them all, but right now let us take up for our elaborate discussion what will happen if the force is applied at its own frequency, the driving frequency. Let us take it up for discussion further. In the second case, where the applied force is at its driving frequency, namely omega d, then what will happen? So, the terms are slightly rewritten and applied force is written on the right hand side with this omega d, because now we are taking the second case, the driving frequency is different from the natural frequency. We have this equation, this is again a second order differential equation. I do not want to get into the mathematical aspect of it, that has already been done in the lectures. Now, we are familiar with this form of equation, we need to get a solution for this equation. In a mathematical way, when we try to get a solution for this second order differential equation, there are two distinct parts present in it. Let us have the general equation what we have. X is the solution that has got a transient part present in it and also a steady state part present in it. There are two states. In the damped oscillation case, we did not have this external force term. So, we had only the transient term. This is actually indeed the damping part. Transient means for a while, it will be existing for a time being. That is the case of the damping, but because there is a external periodic force present in this case, it has a second part of the solution, that is called the steady state solution. Without getting much into the mathematical part, we directly take the physics expression. There are two terms, but we need to have a detailed look at the equation. See, this is how the transient and steady state expressions will appear. Initially, the oscillation is somewhat complicated for some time because of the presence of the two terms, transient part and also the steady state part. The transient and steady state parts of the solution will look like this. Now, when we carefully look at the transient term, see, this is again a damping part, it is a damped oscillation only. The e power minus gamma t is there, the gamma has got its own expression and ah has got its own expression. I do not want to get into all the mathematical parts, but try to explain the physics of this equation, and omega dash has several terms present in it. So, what in general we need to understand from the given equation is the transient part will exist for a while, because e power minus gamma t is present, it is exponentially decreasing function. So, the oscillation will come to stop if that one term is present, but along with that the steady state part is there. So, initially the oscillation will have a complex form, there will be a jerk, there will be a change in frequency, all that will happen when we try to supply the energy from the external force. But after the transient part ceases, what is likely to happen? That is what is quite interesting. Let us try to understand from the equations that we have at hand. This is the explanation we have for the transient and steady state part. The transient part of the solution is the undriven damped oscillation, and as such can be done under damped, over damped and critically damped, because the e power minus gamma t governs it. The steady state part of the solution is determined by the driving force and is independent of the initial condition of the motion, because this will sustain, this will exist for a long time, that is why the name is steady state part, it will exist, this will only last long in the oscillating system. Now, in the long run what will happen? The transient term will die. In the long run the transient part will die and the steady state part will sustain the oscillation at the driven frequency. Who will dominate at the steady state part? it is the driving frequency omega d. The amplitude of the steady state is looking like this. Just for the explanation sake, I have highlighted the other terms present in the term AS. This has got the natural frequency of the system and the driven frequency at which the force is applied, and also the term B. Here B is the damping coefficient and the mass of the oscillating body and the force that is externally applied, all that are present. So, in general, this amplitude of the steady state system is a function of the driven frequency, and we know what is the natural frequency. The omega naught is the natural frequency, which is square root of k divided by m. K is the spring constant and m is the mass. So, omega naught is the natural frequency. This equation gives us a good insight in the steady state expression, or that term also has got the other factors present in it. The driven frequency is there, natural frequency is there, damping constant is there, all these are present in the amplitude. Suppose the damping is very less, the B will be very less, because we are now familiar with the damped oscillation. The B is the damping coefficient, or it is called damping constant. If the damping is a mild one, very mild form of damping, then B will be very less. In that case, we can take up some of the special cases in the equation. Let us see what they are. We have rewritten the equation with small damping. Let us assume the B is approximately 0. What will happen? The equation gets modified like this. See, this is the original equation, for reference I have given. If this B becomes 0, it is in the numerator of this term in the bracket. So, this will vanish. So, the remaining terms only will be present. Now, we have the omega naught as usual as the natural frequency. So, there are two terms present in the denominator. One is driving frequency and the natural frequency. So, it is a chase between the two frequencies, the difference, which will dominate, which is going to rule the oscillation. Is it the natural frequency or the driven frequency? There will be a competition between these two. Now, also we can take up the special cases, like take for example, if the driving frequency is equal to the natural frequency. That is why I have shown the two terms as equal. So, we are going deep into the concept, a special case within special case. The denominator will become 0, the equation gets modified because these two are equal. So, the denominator will become 0, anything divided by 0 is infinity and the amplitude becomes infinity. We need to discuss about this amplitude becoming infinity elaborately. So, if the driving frequency matches with the natural frequency of the system, that too with a very mild damping present in the system. Mild, when we say it is almost 0, that means no damping, which is an ideal case. The amplitude goes to infinity, that means the amplitude is very high, very large value, and huge oscillations are likely to happen. We will continue the discussion of the large oscillations possible, but before that I would like to address an important thing. If the driving frequency is not close to the natural frequency of the system, what will happen? The denominator term will not become 0 and there will be a amplitude present and the driving frequency will dominate. The oscillation will slowly come to settle down with the driving frequency. The oscillation will happen at the driving frequency only, but it will take some time. That is why it is called steady state. How long it will take for the oscillation to settle down to the steady state or the driving frequency, it depends on how much of damping present in the case, that is decided by the transient term, how long it has the effect. That is why it is simply said as it is a complex phenomenon in the beginning, or initially it is difficult to explain. there will be a kind of competition happening between the steady state and the damping, which dominates, and the oscillations will happen in a complex manner in the beginning. But after it comes to a steady state, if the driving frequency is different from the natural frequency, the oscillation will finally settle down to the driving frequency only. But in that, if the special case what we have taken up, the driving frequency matches with the natural frequency, then a peculiar phenomenon is happening. The amplitude shoots up to infinity. That means huge and large oscillations are possible in the system. That is to be discussed further. The phenomenon of increase in amplitude when the driving frequency is equal to the natural frequency of the system is called resonance. So, the resonance is given here as a graph. When we plot a graph between the amplitude and the driving frequency omega d, the amplitude and the driving frequency, we get the resonance curves like this. All the curves have the maximum amplitude at a particular value of frequency. That frequency, when we see, it is the natural frequency omega naught. So, at the natural frequency, the amplitude seem to be maximum, and here we have taken up for 3 types of damping. In the case of heavy damping, the B is not 0, the term originally we have discussed, the B is not 0. In that case, we will have a mild increase in the amplitude. On either side of this omega naught, the amplitude becomes less, because the denominator term will be more and more suppressing the amplitude. Only when the omega is equal to omega d, we have the maximum amplitude. This is a slight damping, still damping is there, the B is not 0, but it is less, that kind of case. And this is an undamped case. See, here it goes to infinity, it is an ideal situation. When will the amplitude shoot up to infinity? The first case, there should not be a damping present, the B should be 0, which is most unlikely in practical cases. All kinds of oscillations will definitely have a damping factor present in it, B will definitely be there. And if at all the B is less, and it is likely to become 0, and second condition, if the driving frequency matches with the natural frequency. So, it is a special case of special case, only in that peculiar case the amplitude shoots up to infinity. Infinity is unimaginable, the frequency, the amplitude goes to a maximum value, that means so total collapse, catastrophe will happen. But because of thanks to the damping that is present, the B is not 0 in any oscillation. So, it will not make the oscillation to shoot up to infinity, but still if the B is less, large oscillations are possible, that also seem to be dangerous in some occasions. So, this graph gives us an insight of how the resonance happens, and there are some examples I would like to give. The result of resonance. Resonance is highly dangerous sometimes. One such example, the Tacoma narrow bridge collapse at Washington, USA in 1940 was identified later for the occurrence of resonance. Mild breeze made a very big bridge collapse because the breeze had a frequency which matched with the natural frequency of the bridge. That is why when the soldiers march on bridges, they are not allowed to march actually. When they cross the bridges, they are not allowed to march on the bridge. They will be asked not to maintain a rhythmic pace. They will be allowed to have their own random pace, so that the natural frequency of the bridge does not match with any one of the marching frequency of the soldier. And also in the case of aircraft wing manufactured, the structure should not match with the frequency of the machinery. The wings only will hold the engines and all for giving the thrust. So, they have the oscillating motions. It should not match with the wing's natural frequency. If that happens, then the wing will start oscillating, it will produce large oscillations, large amplitudes, it will sometimes break the wings. So, when we make bodies, when we make machineries which are likely to work in an environment of vibration, oscillations, we have to be little careful about the resonance part. We should try to avoid the resonance to occur. But in electronic circuits, these resonances, resonance frequency have their own advantages also, which is beyond the scope. So, as a session summary, let us see what all we have seen in this lecture. In this lecture, we have seen the concepts related to forced oscillations, the transient and steady state parts present in the general solution we are obtained for forced oscillation, and also the phenomenon of resonance. We have seen the initial part of the resonance, the shape of the curve, the graph is governed by another term called Q factor. All these are yet to be learnt. So, before we conclude this lecture, let us test our understanding by answering these questions. Discuss the concepts of free and forced oscillations with examples. How do we obtain the transient state and steady state solutions in a forced oscillation? Explain the concept of resonance with examples. So, we have actually learnt the concepts of resonance. The resonance is to be learnt elaborately, maybe with more visuals and more examples, the advantages and also the disadvantages of resonance. We have just got the introduction and the initial understanding of resonance. In the upcoming lectures, we will be able to address to the special cases possible in the resonance. So, with this I would like to wind up today's lecture. Thank you for watching this lecture.